Jim Hendershot again here. We're going to look at lecture number 17 here, which is entitled Polyphase Induction Motor Theory. But let me qualify that by saying this theory is not going to be this theory discussion is not going to involve a lot of mathematics calculations and solving. You've already done all that. We're going to try to conceptualize the theory behind these machines to make it a little easier to get your arms around. Let's see how that goes, see if that appeals to you. In simple terms, the basic principles of how induction motor works is you have stator phase windings, usually 3 of them, supplied by AC voltages at some known frequency, known or specified or controlled frequency. The result is the resulting sinusoidal field created by the AC voltage results itself or manifests itself in both the stator and the rotor. It's the stator, as we've said before, becomes the primary winding of a transformer, and the rotor is the secondary. So these sinusoidal rotating fields are created in both the rotor and the stator. The rotor physically rotates slower than the rotating field in the stator, which causes current to flow in the cage of the rotor, which produces torque from the flux linkage of the rotor and the stator. All resulting performance depends on the slip, which is the stator field RPM versus the rotor RPM for grid-powered motors. And the slip is not controlled in grid-powered motors as an input parameter. It's a result of the load applied to the motor. So there's very limited control, and a specific torque-speed relationship results from that load-controlled slip. So grid-powered machines have no slip control except from the load. Inverter-fed induction machines control both the magnetizing flux and the torque current, the current value that produces torque, so the slip is not directly involved. The slip is still there, but the slip is controlled. And essentially, it's maintained to be constant. That's how you control it, by deciding what the slip should be, which determines how much torque you're going to produce, and then you keep that slip constant throughout the speed operating range that you wish that torque to be constant. So the power factor is a function of the relationship between the magnetizing current and the rotor producing current. That's what the power factor becomes in an induction machine. As I said before in an earlier slide, I like to think of a asynchronous machine or induction machine. It's a synchronous machine wannabe. It's trying to always run at synchronous speed, but it can't quite get there. The rotor runs at some speed less than the stator frequency speed, and this is what is known as the slip of the rotor poles on the surface of the rotor. The magnetic field of the rotor is induced by the difference in frequencies between the stationary winding and the rotor slip frequency. Therefore, the shaft speed of the induction motor, or asynchronous motor, is controlled by the stator phase frequency, with slight variations or reductions caused by the rotor slip. Without separate magnetizing current control, the rotor current varies with slip and load, resulting in less than optimal torque versus speed relationships, as we've seen and studied. So the rotating field in an induction machine is created by a balanced 3-phase stator windings that are mechanically, physically displaced in the stator core 120 degrees apart from each other. And these 3 phases are fed by balanced 3-phase AC voltages. A rotating magnetic field with constant magnitude is produced. And this rotating field in the stator rotates with a speed in accordance with this formula. 120 times the frequency divided by the number of poles. And this gives you the speed of the stator in RPM. But that's not the speed of the rotor. That would be the synchronous speed of the rotor if it had zero slip and it could keep up with it. The perfect ABC sinusoidal wave shapes are plotted here, and you can see they're exactly 120 degrees apart. And at 0 degrees they look like that. 90 degrees away they look like that. And to control them, we can't deal with them. We have to use transformations to transform these currents into D and Q axis coordinates so that we can control the machine the same way a brushless motor is controlled today. So you have to transform 3 vectors into 2 vectors. We've considered this simple transformer before, and that's why it's such an elegant machine. We have a primary and a secondary wound around this core, and the voltage of the 2 windings is proportional to the turns ratio. In a normal transformer, in our induction motor, our shorted secondary, you see in this slide here, only has 1 turn. So the torque is controlled solely by the current, and a 100-volt motor's got a 1-turn rotor, and a 1000-volt motor's got a 1-turn rotor. They're both the same. The shorted secondary it can be considered as a single phase in the equivalent circuit diagram. But with a mechanical manipulation of this picture, we can turn this into a round rotor with the secondary being the rotor inside the primary, which is the stator. Now the torque is produced by the magnetic field that cuts the rotor windings and produces an induced voltage in the cage, which is short-circuited. That's assumed. The resulting rotor torque from the induced voltage produces the second magnetic field. A torque on the shaft is produces the second magnetic field. So the torque on the shaft is produced by the linkage of those 2 fields. And we see that here, torque equals a constant times the B rotor field times the B stator field. The speed performance of an induction machine is to be had a look at now. The rotor cannot run by itself at synchronous speed. We've covered that, or at the same speed. That synchronous speed is the speed of the rotating stator field. Otherwise, the rotor would appear stationary in terms of the stator B field, and would not cut the rotor conductors, so zero current would flow in the rotor, so you would get zero torque. You've got to have slip so that the rotor conductors cut the B field in the stator. That's what the slip does. When the rotor field falls below synchronous speed of the stator field, the stator field cuts the rotor conductors and produces torque. The result is a rotor always runs at a speed less than synchronous speed. The difference in these speeds, we've said, is over and over, is called the slip. Synchronous speed, actual speed, and slip. Synchronous speed equals RPM equals 120 times the frequency divided by the number of poles, which is 2 times the number of pole pairs. For inverter control, the more useful form of this is to solve for frequency. So frequency equals the number of poles divided by 120. Since the rotor RPM is less than the stator field, the rotor is said to slip, as we've said. Therefore, slip can be expressed as the stator field subtracted from the rotor field divided by the stator. No, the stator speed, the stator RPM subtracted from the actual rotor RPM minus the rotor RPM divided by the stator RPM. For motoring, this will be a positive number. For generating, this will be a negative number. Now the frequency from that formula as a function no, the RPM as a function of the number of poles and the frequency from that formula is summarized in this chart for 2, 4, 6, 8, 10, 12 poles for 50 hertz and 60 hertz. This is, however, an induction motor that's run by an inverter can run at any frequency. The frequency controls the speed, particularly if the slip is kept constant. Here's our familiar plot of the speed versus torque curve and the fan load. We've gone over this before. You can have a very simple inverter, an open loop inverter, that controls the ratio between voltage and frequency. And therefore you don't need any feedback device. You don't need any tachometer on the rotor to measure the speed. You can run this open loop as long as you keep the ratio of the voltage and the frequency the same. And that is in a sense what that's doing at all these different speeds. At different speeds you have different frequencies. At different speeds are caused by different frequencies. That's why we have these families of curve here. And you notice the slope of the slip is the same for all these curves. And the reason is because we've kept the ratio, we reduced the voltage as we reduced the frequency to keep that ratio constant. So the slip is always constant, except when you get to real low voltage. Now that constant ratio doesn't work anymore. The torque begins to drop off, so you have to give it a little voltage boost down there. And so this allows the motor with a variable frequency and voltage, but at a constant ratio, this allows the motor to operate at all these different speeds, anywhere inside the envelope of that family of torque speed curves that have been, or speed torque curves that have been identified there. The drawback to this kind of an inverter, a constant volts to hertz inverter, is that you don't have very good control at real low speeds, close to zero, and you don't have high starting torque. You have to have a flux vector drive to overcome that problem, and that's a closed loop volts to hertz drive. And when you use a flux vector drive, you can actually morph the induction machine into a variable, to becoming a variable speed DC machine, where you control both voltage and frequency, and you can operate, well, with the fixed ratios you can operate from about 5 hertz up to base speed, but if you have a flux vector drive you could go right down to zero frequency, zero speed, because there are two control loops that are maintained at the same time, RPM and flux. You get very tight speed regulation, 0.05% steady state error, direct torque regulation, torque control from 0 to 100% torque, control at zero speed, you can generate as much as 300% peak torque at zero speed, and for some applications that require that, high 15 hertz response for rapid load changes. These are all possible with a field-oriented control, which is a flux vector drive, field-oriented control. You're controlling the magnetizing flux, breaking down that phase current vector into two vectors and controlling the magnetizing current, which results in controlling the magnetizing flux. But to take great advantage of these kinds of drives, particularly the field-oriented control, the rotor is best optimized for low resistance and be able to have thin enough lambs and properly insulated against eddy currents to have to use for flux vector control, and the right balance between the cross section area for the copper and the iron, so that you can apply maximum magnetizing current and run the saturation in the resulting steel portions of the rotor right up close to saturation. This is how you get peak torques in in an induction rotor at low speeds, which is necessary for IPMs or for competing against IPMs for traction drives. These machines, of course, can be field weakened, or you can at least get the results of field weakening. Here's a whole family of torque speed curves that each one of these plots here represents a fixed volts and frequency, and you can make a number of these to create a envelope of performance of torque versus speed, such that you can develop a continuous constant torque region and a constant horsepower region, as long as the desired envelope of performance falls within the maximum capability of that particular machine and inverter. And field weakening is required to get the machine to put out power at high speeds, and this can be looked at this way here. For example, a 60 hertz motor can only develop 44% of rated torque at 90 hertz and 25% at 120 hertz. That concludes this lecture. Thank you very much.